So my idea around why are we making this class in probability and representation is that there are a lot of problems that are called like where people search for universality. Like you search for some behavior or some model or mathematical object, which is a bit universal, like several different mathematical objects, maybe in some limit or in some regime will behave in the same way. And then this is, say, one problem, yes? And then you want to, in some sense, characterize what way, how do they behave, for instance, or how to characterize them. And what is nice is that if there is a universality class, if there is a group of objects that are supposed to behave the same, it's enough that you find one for which you can compute. Здравствуйте. Да, нормально. Да, спасибо. Да, все отлично, спасибо. If in this class that is supposed to behave all the same, you can compute for at least one object this behavior. Then you can compute for all the others if in the limit is the same. Let's make a very toy example, yes? Toy example, and this like universality versus computability. And this example is a very famous theorem in probability, which is central limit theorem. Теорема центрального определения. You know what is central limit theorem? Yes? Is it clear? So this means that if you have, of course, it's much more general, yes? But if you have a family of IID random variables, so that's yes, to example, if you have central limit theorem, центральное определение. Вы помните, что это? You remember this theorem, yes? It's clear for everybody. So if they say that the expectation is 0 and the variance is 1, the expectation is 1, then you know that if you take the limit of the sum of these random variables, this converges to in law to a normal Gaussian random variable. Yes, you remember this theorem in law. So how can we? Of course, there are many proofs of this result, but I just want to make a very simple example what I mean without this universality and computability. So first, there is a case where it's very easy to compute this limit, and this is the case where the xi are already Gaussian. Yes, because first there is a very algebraic characterization of a Gaussian distribution, like a fixed point of convolution. Yes, if you have, say, two random variables, okay, up to homothetic transformation, if you divide by square root of 2, if they are independent and Gaussian, their sum is still Gaussian. Okay, so this has the same. If they are IID, this has the same law of x1 and x2. This you can make like, okay, even if you don't know Gaussian distribution, you can just look for fixed points of convolution. Like you search for random variable whose law of the sum is equal to the sum of each. If they're independent, is equal to the law of each of them. Okay, and so this is so okay. This also works for any n. It also works for any n. So if the xi are Gaussian and IID and so on, then this limit, we can compute it explicitly. This converges because it's already the same for every n, the law, to a normal, okay? So they're already normal. And n01, the Gaussian, this means that they're, is this notation? We will never use it, it's just in this example. This means there's a Gaussian random variable with mean 0 and variance 1. Okay, now what do I do if the xi in this example are not Gaussian? So here I just, in the Gaussian case, I can compute. And then I can, but if I think that this the behavior of this object is universal, it behaves in the same way for many different random variables, okay, I do not need to compute in the general case. I can just compare this case with the Gaussian in the following way. You know that to show convergence in law, it means that the expectation of every smooth function converges. Yes. So I just want to understand that the expectation of a smooth function of this sum. Well, now the xi are, yes, IID with expectation is maybe 0, or it's not even important. IID with finite second moment. Okay. So how do I do? And I want to compute the limit when n goes to infinity of this expectation when f is a nice function. Well, I can do a very simple, it's just a toy example, yes? A very simple lemma. If I have 3 random variables, x, y, and z, let's say independent. And I take f C3 function with bounded derivatives of R. And I say that I call the constant is just the supremum of the third, is the norm of the third derivative. Okay. Then if I do the expected value of x plus y minus x plus z, this will be less or equal than constant over 3 factorial 6 times the expected value of y to the cube plus x to the cube. Why? It's just Taylor formula, yes? F of x plus y minus f of x plus z for any 3 numbers, not variables, 3 numbers, x, y, and z. This is, okay, if I do Taylor's formula, this is like f of x goes away on both sides because there is minus. So it's f prime of x, y minus z, plus 1/2 f second of x, y square minus z square. Yes, I'm just doing Taylor's formula around y equals 0 and z equals 0. And then there is a remainder, but the remainder is bounded by constant over 6. Oh, sorry. So here I will need that the expected value of y, sorry, is equal to the expected value of z, and the same for the square. Otherwise it will not work. I'm sorry. Okay. And so this will be less than y square, y cube plus z cube. Okay. This is true for any yes, where this constant is exactly the third derivative of f. Okay, 6 is 3 factorial. Okay, so plus r, and so the rest is bounded by this. Okay, but then if I take the if I compute this, where small x is x of omega, and small y is y of omega, and small z is z of omega, and I integrate. Yes, if this is true for any 3 numbers. So it's true if I put here random variables, and I take the expectation since x and y are independent, the expectation of this is 0. The expectation of this is also 0 because the expectation of y squared is equal to the expectation of z squared. So only the expectation of the remainder remains, which is bounded by this. Okay, so okay, this is just a very simple fact. But then if I have to do the expected value of f of 1 over square root, so I can this function, yes, here. So proof of a central limit theorem, like using this fact that I computed it for Gaussian, and now I claim some universality. How I do it? Here I do square root of n sum over xi minus the expected value of f, and now here I use I compare it with the sum of independent Gaussian random variables. Okay, let's call them zi. I want to check the limit of this. Okay, the limit of this I already know because this is Gaussian, so this is just the Gaussian integral. This is the same for every n. The zi are IID Gaussian random variables. It's okay. So okay, this is less or equal than then. Well, you see, I just every time I use this little lemma to substitute one term in the sum. So I have the sum of xi, and every time I change one xi in one zi. So I apply that lemma with, I don't know, first times with y equal to x1 over square root of n, the second, and I change it to z over square root of n. The second time I applied with x2 over square root of n, and n times I replace all the terms in the sum with that are here with the sum that is here. You want me to write it? Okay. Then this will be smaller than, say, the sum of j from 1 to n, the expected value, so of 1 over square root of n. And instead of doing, so I replace up to j, so let's say zj, z1 plus zj plus xj plus 1 xn minus the expected value. Maybe I can erase all this. F of 1 over square root of n z1 zj plus 1 plus x, okay, j plus 2, say up to xn. Yes, because, okay, if I remove the absolute values, you see, every time I just replace one j with the next, so I will get this minus the, well, okay, j should start from 0 to n minus 1. It's like I write this sum every time changing only one variable x to one variable z. Okay, so every time you see in the sum I replace one xj with over square root of n with another xj plus 2 over square root of n. So this is less by the lemma than the difference j to n, and so each of these terms is bounded by constant over 6, and then there is the expected value of x, okay, j, what I substituted, j plus 1 to the cube over square root of n to the cube plus the same thing, y, j, z. To the cube, provided, of course, I took z with the same expected value and the same variance as x. Okay, so I can apply the lemma. Okay, then this sum, they are all the same this time because they have the same distribution, which is, so this expected value is oh, sorry, the cube. Okay, I'm assuming the third moment is bounded. So this is a factor n. These are square root of n to the cube, so it remains 1 over square root of n, and then, okay, there is some numbers. Yes, these are all the same for all the j because they're all the same distribution. So, okay, here there is some numbers times twice the third moment of this plus, okay, another constant. Okay, so you see that for this sum, I didn't compute anything in some sense. I just say that it's close to this. And for this, I could make an explicit. It's just it's a toy example. It's not what I want to discuss, but it's like this idea that I have some object for which I can compute something. For instance, in this case, its limit of the central limit theorem for Gaussian, which is trivial. But here, the computation for Gaussian is purely algebraic. Okay, I look for fixed point of a convolution and of a measure with itself, and then this gives me Gaussian if you assume that the second moment is finite. And then I just make an analytical computation, yes, where there is a remainder and something, and that goes to 0, and then I find the same results for a large class. So the central limit theorem is like universal. Okay. So I want to discuss, start discussing a different example of this. So this example is just an example. Okay, we will never see, but so a different example where. Which is, say, the earth of a lot of research currently, and this, like, how it's done typically, yes, like the spectrum of operators. You have a linear operator, for instance, the Laplacian on a domain, or some Schrödinger operator, and things like this. And how is, I don't know how to say, what are the features of this spectrum? Like, you take the n eigenvalue of the Laplacian, when n is large, how does this behave? What is the gap between the n and the n plus 1 and things like this? Yes, you understand the idea. I have an operator, linear operator on a space, say Hilbert space. It will have a spectrum, like the set of its, say, eigenvalues points. For instance, if it has compact resolvent, I don't know if you ever seen these ideas, but like at the end of the day, what is the question? Like, how are done the eigenvalues of a large matrix? Yeah, because an operator is like an infinite dimensional matrix. So you take a very large matrix and how are done its eigenvalues, how they behave typically. This kind of question. So how they behave, it means a lot of things. It can mean, I don't know, the largest eigenvalue, what is it? Or how it goes when n is very large? Or what is the distribution of all the eigenvalues, the multiplicity, or are they close to each other, far away from each other?
What is in this case, in case of operators in some Hilbert space? And what? Oh,
okay. So okay, like suppose that it's an example. Suppose that you have, say, a positive operator, for instance, or bounded from below. And say self-adjoint, okay, and maybe with discrete with point spectrum. So you can order the spectrum, the smallest, the second smallest, the third smaller, the fourth small, okay? And then you take n large, the nth eigenvalue, how it behaves. Of course, like this, you can find operators with any spectrum. It's not that there is an answer, yes? But say, for instance, I don't know, I can give you a picture in R2, and I give, Laplacian with this boundary. The Laplacian with zero condition at the boundary. Yes, it is clear. This is an operator which has if this set is bound, is an operator which has purely discrete spectrum, and you can wonder how it is done. Of course, it depends on the shape, but the idea is that indeed there is a universality. If this shape is not too bad, is smooth and generic, maybe convex, then when n is very large, the behavior is the same no matter what was the shape. So this is not, again, what are there some cases where we can do a more or less explicit computation? And of course, it's matrices, okay? So I want just to take a matrix, a large one, with entries, okay? And try to understand how is done the spectrum. Of course, if I take, I don't know, all ones, 0, 0, then there will be 1 and all 0. If I take other numbers, other numbers. So if I want to, if I have any hope to catch some general behavior, I will take the entries random, okay, and then try to understand, hope that when n is larger and larger, some feature of the spectrum will be the same, no matter what is the distribution of these numbers. Okay, so like I give you a matrix. Here I write random numbers, and when the matrix is very, very large, the eigenvalues they feature some behavior which doesn't depend on the distribution I chose for the entries. Is this yeah,
it is clear.
It's clear, yes. Okay, so okay. So to have something to work with real numbers, we could do also without asking symmetry, but it's slightly more complicated. So I will write here like x11, they will depend on n, yes. x1n, which also depend on n, and so on. X and n, and n, x what is it, n1. This is my large matrix, and these are random variables. Okay, xij are random variables. But I'll take it symmetric, so that the spectrum is purely real. Okay, by spectral theorem. You understand what the spectrum, yes? Substituение is equal to xji, so that these are like it's asymmetric, yes. But beyond this, so for I bigger, so if otherwise beyond except this, they will be independent. Now, if I take all with the same law that doesn't depend on n, the spectrum will explode. So I will take xij in this way. xij, I will take it. So I will take xji equal to xij. I need to choose how they scale with n. Okay, if I do not divide them by the correct number that depends on n, the spectrum will just explode. So since I want to catch limiting behavior, I need to catch the right scaling. So I will take here 1 over square root of n, say some yij, if say I is more than j, and 1 over square root of n zi, if I is equal to j. And so these are all independent. These things are all independent, this and this. But yij all have the same law, which over some random variable y. Okay. And so this is on the diagonals, there are this zi over n. And off diagonal, there are this y. So, and also all the zi, they have all the same distribution. Okay. So these are all IID. On the diagonal is all IID. Off the diagonal is all IID, except for the fact that they are symmetric. I could have taken not symmetric and to get also, one could also without symmetry, but let's take the symmetric case. It's a bit faster to compute. And but the law of what is on the diagonal and what is off diagonal may be different. It could be the same, it could be different. You have two random variables, okay? And I will assume that the expected value of y, so there, is 0. That the expected value of z is also 0. And the expected value of y squared, I will take it equal to 1. Of course, if it's not, I don't know, if for instance you change z wasn't 0, you are just adding something on the diagonal, you just shift the spectrum. That's, I mean, it's not a very, this you will just change by a small rank matrix. So these are not big deal. Of course, if this is not 1, it's 10, the spectrum also changes just by a factor. So that's, this is just a normalization, how to say, up to linear transformations, you can reduce this case. And let's say that also the expected value of z squared is at least finite, okay? So there are many features that one can study of the spectrum. For instance, when n is large, how does the largest eigenvalue behave? The second largest eigenvalue, the gaps between the spectral gaps between eigenvalue. So today I will look at the first result in this context, the most classical, and is how altogether this eigenvalue behave when n becomes larger and larger. So I will look at the following object, which is random, okay? Given n, I will look at what's called the spectral measure. So if you know what's a spectral measure for operator on Hilbert space, it's not exactly this, because there are projectors also. But okay, then it's just the base of the spectral measure, to be really precise. But it's just this delta over lambda I. Let's check in a moment what it means. Okay, where lambda I are the eigenvalues counted with multiplicity of the matrix xij. Okay, so what I do, I randomly throw n squared random variables with this independent, with this distribution, and I will have n eigenvalues because this matrix is symmetric, so there are n eigenvalues. If I count them with their multiplicity, I have n eigenvalues. And I make a probability, so this is a probability measure on R, but it's random, okay? It depends on what numbers appeared here, okay? How is done? When there is an eigenvalue, I put a little probability, a little weight, 1 over n. Okay, so this probability measure is discrete for every n, okay? It's concentrated on n points, or maybe, okay, some of these may coincide, but it's like, here there is this point, if this was an eigenvalue, had probability 1 over n. This is another eigenvalue, also this point has probability 1 over n, and so on. Okay, but they are random. Okay, so this is a probability, but you shouldn't think that it's a probability. You should think that this is the object we look at. This I could have looked at 5 times over n, and I will get a measure of mass 5. It's not important that is So the randomness is not in this probability, it's in the law of the xi, and so it's in the law of the lambda I, okay? So okay, just by convention here one puts 1, but don't get confused that this probability is associated to randomness, okay? This is a probability measure, but it's just the object we look at, okay? It's just a distribution of weight on the real line, okay? You have n small weights, each on the position of each eigenvalue. And now n it becomes larger and larger, larger and larger, and you want to check what is the limit of this distribution of weight, okay? So so we want to prove, not in this generality, this theorem, which is the following: pi n, when n goes to under this hypothesis, when n goes to infinity, when n to infinity, pi n converges to the semicircle law. I write in a moment what it means. Semicircle law, almost surely. So what does it mean? It means the following thing. This means, so first, so the semicircle law, let's give a name, sigma, which is also a probability measure on R, okay? This is a sequence of random probability measures on R that converge to a probability measure on R, which is not random, it's deterministic. So it's a sort of law of large numbers. In the law of large numbers, you have a sum of n random variables. This converges to a deterministic number. Here you have a probability measure. It converges to a deterministic probability measure, okay? And sigma is very explicit. So who is this probability measure? It has a density. Okay, on R is a probability measure which has a density, and is written like this: 1 over 2 pi, the square root of 4 minus x squared, okay, provided x is less than 2, dx. So this is R. You put 1 over n on each eigenvalue. When n becomes larger and larger, you, like all these points becomes, this law becomes more and more continuous, okay? And the limit has a density which is like this. This is just this picture. But this is the density, okay? Yes, so 4 squared. So this is minus 2, 2. Okay. So, and what does it mean? So in the sense, so where sigma is this? So what does it mean? Converges almost surely for probability measures. So these, so I don't know if you could state it in Wasserstein spaces here, if you know what a Wasserstein space is, or this just means, if you want, that for each function f, which is continuous and bounded on R, the probability that the limit when n goes to infinity of pi n of f, so this means the integral of f with respect to this measure, is equal to sigma of f. So this probability is 1. So this is the integral, yeah? For a measure, I will denote for a measure pi of f, the integral of f in the pi. So pi n of f, if f is that thing, just means 1 over n, the sum of f of lambda I. While sigma of f is just the integral of f of x, square root of 4 more x squared dx over 2 pi. Okay. But you could, this is equivalent to say that a suitable distance on space of probability measures converges to 0 with probability 1. So like you have the space of probability measures on R. Here there is this point sigma, which is this semicircle law. Okay. And for each n, you have some random point. For n equal 1, okay, there is delta on the unique eigenvalue of a 1 by 1 matrix. For delta, for n equal 2, you will have 2 eigenvalues, and this is probability 1/2 is one eigenvalue, probability 1/2 is the other eigenvalue. When you have n eigenvalues and a matrix n by n, okay, with probability 1 over, this is the probability measure that gives probability 1 over n to each eigenvalue. Okay, so n becomes bigger and bigger. This is random because it depends on what your random variables were. Okay, but when n becomes larger and larger, with probability increasingly close to 1, you will find it. You will see that this sequence converges to this point of probability 1. So you see, no matter what was the distribution of this xi, we took it idea. One could make. There are many different models for which something like this is known. The limit is always this. Okay. If we didn't take complex, if we didn't take the symmetry, eigenvalues would be complex, and the limit would be a probability measure on the complex plane, which is just a uniform on the circle of radius 2. So you see that this comes from the fact that when you then by symmetry symmetrize, it's much more likely to be around 0 than to be around 2. While the probability that you are away from 2 is very small. So is this interesting, this object, or not? Well, of course, you see more or less where all the eigenvalues go. Yes, all like this. Nobody more than 2, more or less, and so on. But this doesn't tell you anything on a single eigenvalue. Yes, because the weight of each eigenvalue is 1 over n. So a fraction, I don't know, less than like it only cares where, I don't know, order of n eigenvalue go. Yes. I don't know, it doesn't, this result doesn't tell us anything about the largest eigenvalue, for instance. Because, okay, the largest eigenvalue here comes for 1 over n delta over the largest. When n goes to infinity, average of smooth function, okay, there is 1 over n f on the largest eigenvalue. F was bounded 1 over n. So I cannot say anything about a single eigenvalue. It's just global behavior, yes? Okay. So, but still, it's a nice result due to Wigner. This theorem is due to Wigner. But okay, so we will check proof of, but with more hypotheses. So this theorem has a long story. It's Wigner first proved for where these random variables were Gaussians, this y and z. But so okay, let me write what we will prove, because this theorem like this is very hard in reality. And I'm absolutely not an expert in this field. I just heard about it I never. Okay, but this theorem, so the theorem, as I presented in reality, is quite hard. So we will assume much more. So we will prove it. So what we prove? First, we assume that the expected value. So you remember, yes, xij was okay, 1 over square root of n. If I don't put 1 over square root of n, it's like this side, the semicircle has size 2 square root of n. That's why so to make it converge, I just divide by square root of n. That's like if I divide by something smaller or something bigger, it will. So if I divide by more than square root of n, the limit measure will be all concentrated in 0. If I divide by less than square root of n, there is no compactness, there is no limit. Okay. In the space of probability measure. So 1 over square root of n, some yij, and this y, they all have the same distribution, and 1 over square root of n is at I. So this was I bigger than j, and this was for I equal to j. Okay. So we will assume that this random variable, so they all have the same law of some y and some z, and we will assume that all these things are finite. So, and also we will not prove almost sure convergence, we will prove convergence in probability. Namely, we will prove not that the distance, the probability that the distance between sigma and pi n goes to 0 is 1. We will prove that the probability that the distance is bigger than epsilon goes to 0 for every epsilon, yes? So if we just rephrase this weakly with this continuous function, we will prove that for every function continuous and bounded, or actually under this hypothesis, we can also equivalent say for every function with the at most polynomial growth continues with at most polynomial growth. So this, if you know, this means also Wasserstein P for every P. I don't know if you ever seen Wasserstein spaces. The limit when n goes to infinity of the probability that the average of f for pi n minus the average for the semicircle law is more than epsilon, this limit is equal to 0 for every epsilon. We could introduce a topology on the space of probability measure and check that this means that we converge in probability to this limit in this topology. But there is no need to. What it means is this: it's clear that integrals of functions identify the probability measure. So this really means that yes, that is a limit. Yes, it really tells us that these eigenvalues in the limit make this picture. Okay. Okay, so going from improbability to almost sure, it's very easy. That's not the problem. The problem is if you want to decrease this hypothesis, okay? Because Wigner proves for Gaussian, so in particular it's true for every k. If you want to go only to k equal 4, this is not so hard, but you say more or less we could do it with the same tools. Then with some work, it's enough to check 2 plus epsilon. Like you need that all moments are finite, but a bit more than 2. 2.1, I don't know, 2 plus a bit more than 2. And if you want the minimal hypothesis, the one in which I wrote the theorem, k equal 2, this is 10 years ago, Van Wu and Terence Tao proved it in a very famous paper. So it's one of the famous results of Terence Tao. Can you imagine how hard it is to go to k equal 2? Because there is some really crazy combinatorics and number theory enters. I have no idea how. I heard once of the proof for k equal 2 works, but it was more than 10 years ago. I completely forgot. It's very hard to do the case k equal 2. Okay, so and of course, if k is less than 2, there are also results, but the limit will not be semicircle law. So if the second moment is infinite, even the central limit theorem you have to modify. So it's clear that the behavior should be a bit different. Okay. Okay. So here, beware. These again, our random variables are independent, but these eigenvalues are all but independent. Okay, they are the zeros of the characteristic polynomial, which depend. So the coefficients depend on the random variables. They were independent, but then there is this very complicated functions that takes a polynomial of degree n and gives you its root. It will never. These lambda I, they are not independent. Indeed, one of the interesting points is to understand how they influence each other. Yes, maybe we will see this later. Okay, so that is our task, is to prove this theorem, but with this more comfortable hypothesis. This, okay, it's probably almost sure. It's easy to go from here to almost sure. It's not where the difficulty go, but who cares to improve this little improvement? Here, not to assume that all the moments are finite, but just to assume some moments, the combinatorics becomes harder. Okay, so we take this comfortable hypothesis, but it's not. Okay, so what I really want to show is so there are two things, like for the central limit theory, in some sense. One, it's algebraic computation. Let me come out how does it come out this circle? Yes, from where you have a large matrix, eigenvalue, characteristic polynomial, compute it. And then there is another part that is like, okay, once you really compute algebra, like with the combinatoric argument, these things check that the difference goes to 0. I don't know how to say. Okay, so there is a combinatorial part, like a clean computation, and epsilon and delta. Okay, so let's us write. So we prove this theorem. We want to prove two lemmas first that are the key point. The first lemma is the following: that the expected value. Let me write a bit informally. Yes. So pi n was that measure on the function x to the k. Okay. So I should give a name to function power and write here pi n of that function. Let me write the variable x to the k. So this just means 1 over n sum of lambda I to the k. Okay. Clear? Yes. Okay. This converges to sigma of x to the k. So this just means the integral of x to the k square root of 4 minus x squared between minus 2 and 2 over 2 pi dx for every k integers. So, and lemma 2, the probability that pi n of x to the k minus the expected value of pi n of x to the k is bigger than epsilon. this goes to 0. This limit is always when the matrix is bigger and bigger, and goes to infinity for every epsilon. Okay, so if we prove lemma 1 and lemma 2, let's first check that if we prove lemma 1 and lemma 2, we prove the theorem. Okay, and then we prove lemma 1 and lemma 2. So lemma 2, in reality, there is some combinatorics. It tells us that this sum of eigenvalues to the power k, which is random because the eigenvalues are random, the probability that it's far away from its expected from its average, it's small. And this tells us that the expected value of the power x of this sum is close to the one on the semicircle law. Okay. Then we need, so why these two imply the theorem? Now let's check it, but it's quite clear that it should imply, because once these are integrals, all is linear. So once I know it for powers, I know it for polynomials. But with polynomials, I can approximate functions uniformly, okay, on compact sets. So once I know for polynomials, I know these two things for function, for any smooth function. But you see, so the expected value is close to sigma. The function I'm interested, the random variable I'm interested in is close to the expected value. So Pn of a polynomial is close to sigma of the polynomial. So Pn of a function will be close to sigma of a function, and that's what it means in the theorem. Okay.
But we have all the bounded functions.
Yeah, bounded function or polynomial group. But as we can check, as we will check in a moment, it's enough to make the approximation on a compact set. Because of course a polynomial will not approximate a function on R uniformly, only on a compact set. But this is not a big problem. Okay, so did I answer your question?
Well,
No.
we have bounded functions on real life.
Yes.
And Weierstrass theory implies that we can only approximate on
yes, on a compact set. But then the probability that you are away from a compact set, away from this average, yes, it's the integral is the average over a compact set plus the average away from the compact set. But being away, like the probability that pi n gives away from compact set is very small, that goes to 0 against any polynomial. We will check in a moment this, but yes, you're quite right. First, I need to make a cutoff indeed, yes. So let's first, okay. So let's preserve lemma 1 and lemma 2 maybe. And so let's do a little bit of combinatorics first, maybe. Or maybe we don't need it immediately. Yeah, let's just compute what is sigma of xk. Okay, this sigma of xk, this is the integral of x to the k square root of 4 minus x squared over 2 pi dx between -2 and 2. Of course, this is 0 if k is odd. Yeah, because this is symmetric if k is odd. And okay, I can do, otherwise I can do the change of variable x equal to sinus of theta. Okay, and so this is x to the k, yeah. So here I will get 1 over 2 pi, twice sinus of theta, square root minus, okay? So I will get integral between minus pi over 2 and pi over 2, theta goes to here. So I get a 2 from the change of variable, okay, 2k. And here I get a sinus of theta to the 2k. And then I get, this is just twice cosinus of theta. And from the Jacobian, I get another cosinus of theta, d theta. Okay, then this is 1 minus sinus of theta squared. So you can compute it. I will not do it. It's just an integral. If you know the integrals of sinus of theta to the 2k. Okay, this you can do by induction, doing a couple of integration by parts. Okay, so I tell you the result, then I will tell you also why I remember, but the result is 2k factorial of k factorial times k plus 1 factorial, which we will call it c k. No, sorry. Like 2n factorial over n factorial n plus 1 factorial, which we'll call it Cn, if k is even equal to 2n, okay? Sorry. So x to the 2n. No, if k is odd, it's 0. If k is even, let's write it 2n, and here is 2n factorial.
Cn is
it's a Catalan number. Yes, the Catalan number. That's why I remember this integral, of course. Okay. In particular, you can immediately check, and we will check it in a moment, that this is not bigger than 4 to the n. Okay. So proof. Let's prove a theorem of Wigner theorem, assuming the lemma. Okay. Okay. So then the interesting part is here. Yes. When the semicircle law comes. The rest, I mean, I don't know if it's interesting. This is the algebraic part. This is delta, epsilon and delta, and this is also epsilon and delta. So how to check this? First, let's notice this. That was what you were asking, actually. The limit, we claim that the limit, when n goes to infinity, of the probability that pi n of x to the k restricted, this means that this function is 0 when x is more than a, okay? The probability that this is bigger than epsilon, or let's say bigger than, okay, delta, maybe, or epsilon. This limit is equal to 0 for all epsilon and for all a bigger than 4. Okay, so you see that this integral is uniformly small in n, this average once if you restrict. So this is a sum of eigenvalues to the k, but only restricted to those eigenvalues bigger than a. Okay, so like this is a probability measure. If I look away from the interval minus a, where a is any a bigger than 4, this doesn't count. Okay, so okay, this is like this if you want. Okay, so how to check this? Well, pi n. So the probability that pi n of x to the k, let's write like this, 1 x is bigger than a, bigger than epsilon. So this is a real random variable. Yes, this is a random probability measure. Once I integrate it for a function, it's a real random variable. This is a real number, random real number. Okay, it's the sum of the eigenvalues to the k, or sum of the eigenvalues bigger than a. Okay, so this is a real number. This is bigger than epsilon. This is less or equal than 1 over epsilon, the expected value of this random variable. Okay, so expected value of x to the k 1 pi n, sorry, 1 x is bigger than a. 1 x is bigger than a. Okay, but now I still make a smaller or equal, since this function is 0 when x is bigger than a. If here I put x over a, or x to the k over a to the k. Yeah, because a is bigger than 1, and so okay, it's not important. A is bigger than 1. If this guy is less than, I mean, if x is less than a, this is before it was 0, now it's 0. If x is more than a, before was 1 here, and now it's something bigger than 1. Okay, so it's still, I can put this. So this is smaller or equal than 1 over epsilon. Of course, now if this is all positive, so if I remove this, it's still bigger, okay? So you see that it's 1 over epsilon times a to the k, expected value of pi n x to the 2k. This is a random number. This is a random probability measure. This is a random number. I take its expected value, and I get this. Okay. So now, if I take the limit n to infinity, so I continue here. I didn't want to erase the lemmas, but limit n to infinity of the probability that the moment, but restricted to x bigger than a, is bigger than epsilon. This is less or equal than 1 over epsilon a to the k. And okay, the limit of this thing by lemma 1 was sigma x to the k, ck. Okay, ck is less than 4 to the k. So this is less or equal than 1, so actually 1 over epsilon times 4 over a to the k. The limit, yes? Good, but now look. Okay, if a is bigger than 1, the left-hand side, this, is increasing in k. So if you want, yeah, let's, okay, I'm sorry, I will erase the lemma 1 and write it back to get some space on the blackboard. These are the integrals I can, so we are trying to do this claim. This is what we are trying to prove. First. So if you want, and this is what we got, that this limit that you want to prove is 0 is less than this. Okay. But now, in reality, you see, if a is bigger than 1, the bigger is k, the bigger is this number. So this function is increasing in k. Okay. So if you want, I can also write that this limit of the probability that pi n of x to the k, x bigger than a, bigger than epsilon, this is less than if for each h bigger than k, the same limit of the probability of pi n x to the h 1 x bigger than a more than epsilon. Yes, the probability, if this was bigger than epsilon, also this is bigger than epsilon. So the probability is smaller, which is, however, this is smaller than 1 over epsilon 4 over a to the h for each h bigger than k. But then, okay, if this limit is not 0, I mean, I can take h arbitrarily large and make this as small as I want. So this limit must be 0. Okay, so just because this is increasing in h, this is in k, this is decreasing in k. So I just here can check the next ones and it will be 0. Okay, and now how do I do using lemma 1 and lemma 2? Okay, so recalling this, so we are proving convergence in probability. Yes, we have to prove. So to conclude theorem 1, we need, if you remember, that the limit when n goes to infinity of the probability of pi n of f minus sigma of f bigger than epsilon, okay, absolute value if you want, or change f to minus f, is 0. Okay. Okay. Now you give me f for each f and epsilon. F is smooth or continuous bounded or maybe polynomial grouped, and for each epsilon positive. Okay, what do we do? You give me these things. First, as you were saying, I need to take care of what is outside, like compact sets, these compact sets. So first, I take a function chi. This is a function from R to 0, 1. It's not like this. Yes, okay, say it's 1 between minus 5, anything bigger than 4, and 5. Then after, I don't know, 6 is 0, okay? And minus 6. This is my function chi. Okay? And then I keep this effect here and erase anything else. And then I also take a polynomial P, such that the supremum over all the x, say less than 6 in absolute value of f of x minus p of x is less than delta. And I take delta, let's make it safe, epsilon over 8. Okay. So you give me f epsilon, I can find, okay, chi doesn't depend on f or epsilon, but I choose this polynomial, since on compact set polynomial are dense, I choose that f of x minus p of x is less than epsilon over 8 for every x. Okay, and then I write pi n of f minus sigma of f. This will be less or equal than. Now, I mean, I approximate f with the cutoff with the polynomial, and so on and so forth. So let's hope that I don't make any mess, but I will write pi n of f minus pi n of f times chi. So this is also a smooth function because chi was smooth, but it's supported between -6 and 6. Okay. Plus pi n f chi minus pi n p chi plus pi n, so okay, the absolute value, pi n p chi minus pi n p on the polynomial. Then here on the polynomials, thanks to the lemma, we'll be able to pass from pi n to sigma, yes? So pi n of f minus pi n of sigma, sorry, pi n of p minus sigma of p. And then I have to go back from p to f. So I will put plus sigma of p minus sigma, okay, of p chi, this is actually 0, plus sigma of p chi minus sigma of f chi, plus sigma of f minus sigma of f chi minus sigma of f. Yes, every time I added something, so okay, why is the list is so long? From f, I take it's like f cut it off beyond 6. Then f cut off, polynomial cut it off beyond 6. F polynomial minus the polynomial not cut it off. On the polynomial is where I will pass from pi n to sigma, and then I go back, okay? So the probability that this is bigger than epsilon is less than the sum of the probability that each of these guys is more than epsilon over 1, 2, 3, 4, 5, 6, and 7. Yeah, because there are 3 for f, 3 for pi, 3 for sigma, and 1 from sigma to pi. Okay, but actually, so you see that this guy, let's check that. So this guy is actually 0 because sigma is supported between -2 and 2, and this guy, so between -2 and 2, p and p chi are the same, and this is also 0 for the same reason. So actually, there are only 5 terms. And also, let's check more. With probability 1, this is less than delta. Because this is a probability, random, but it's a probability. And these functions, they are less than delta. When they are non-zero, they're less than delta. And also, this is less than delta. Is the average with respect to the probability of two functions that differ in every point less than delta. Okay, so I don't know where to continue. I continue in here, yes, after here, sorry. I'm managing the Blackboard poorly. Let's continue in here. So the probability, so this probability, which is here, the probability that pi n of f minus sigma of f is more than epsilon is less than okay, these two guys were actually 0, but so is less than the probability that this is more than epsilon over 5 plus the probability. Okay, but delta, So the probability that this is more than epsilon over 5 is 0, because delta was epsilon over 8. Okay, I could have taken epsilon over 5. Yes, this will never be more than epsilon over 5. So plus the probability that pi n of f chi minus pi n of chi is more than epsilon over 5. This is 0, this probability. Then there is this. And so on. I really don't want to spend too much time on this. It's clear that it works, I hope. Then there is the crucial part, pi n of p minus sigma of p, more than epsilon over 5. And the other things, which is delta. Sigma of p chi minus sigma of f chi. This is deterministic, but so this probability is 0. This probability is 0. The other must converge to 0 when n goes to infinity. I made it's a bit technical just because, okay, we do it for polynomial, then f and so on, but it's quite clear. Okay, once you know the convergence on polynomial plus good bounded away from compact sets, the rest it's done. Okay, so then let's check that the other goes to 0. This goes to 0 exactly because of this case, f at its most polynomial growth, and this away from a compact set, like for a equal 6, where this or 5, where this was not 1 anymore. This difference is bounded by a power, suitable power k, is 0 if x is less than 5, and otherwise it's bounded by a power x to the k because f had polynomial growth. So for each epsilon, this goes to 0. It goes to 0 also when it's epsilon over 5. So these two were really 0. This converges to 0 when n goes to infinity, no matter who is f and who is epsilon. The same for here. It's a polynomial cut it off minus a polynomial. Okay, still bounded away from a compact set more than 4. Is bounded by a power. So this goes to 0. And so at the end, we are really, the only term is this, where now we really need our lemma 1 and lemma 2. Yes, this is where I compare pi n with sigma. Okay, I'm claiming that for each polynomial, pi n of p converges in probability to sigma of p. This is a real, for a polynomial, this is a real random variable. This is a deterministic number. And I'm claiming that this number converges in probability to this one. But lemma 1 said that so lemma 2 said that this converges in probability. So the difference between this and its expected value, sorry, converges to 0 in probability. And lemma 1 said that the expected value converges to this number in probability. So since some of variables that converge in probability, this also converges to 0. So this is where we need to use lemma 1, lemma 2, okay? So let's say that x, so yes, I'm applying just the fact that I can write it here in a second. Just that, you know, if I don't know, I have a sequence of random variables that converge to some number u, and then I had un minus some, sorry, small numbers un. It was the expected value of pn converges to sigma of p. Of course, we checked on powers, but then by linearity we know it on polynomials. Then here I have random variable un minus un converges to 0 in probability. Then un converges to u in probability because un minus u is un minus u small un plus u small un minus u. Okay. So okay, this is epsilon and delta, but in reality it's long because it's 8 parts. But in reality, I think it's very clear. Okay, once out of the compact sets there are no problems. We need to prove convergence for functions, but it's the same as to prove convergence for polynomials, and by linearity is the same as to prove, because it's the same to prove convergence for powers. Okay, so in the not so much time that remains, I really want to check now where is this circle coming from. Okay, so lemma 1 in all this story, all the rest is something is small, and the computation was lemma 1. Okay, lemma 1 is where sigma appeared, the circle appears. Okay, so for this there is no, I mean, it's not that we can say here something is small. The limit, we must compute what it is, okay, how these eigenvalues are. But of course, thanks to the fact that we assume that all the powers are finite, it's really enough to calculate explicitly. So let me rewrite lemma 1, and let's check what to do. So lemma 1 was for each k, the limit when n goes to infinity of 1 over n, the sum, the expected value, it was only the expected, so this is a number, the expected value of the sum of the eigenvalues to the k is equal to sigma of x to the k, which was equal indeed to 0 if k is odd, and to ck over 2 if k is even. And okay, where this was k factorial of and so on. That's what we want to prove. Yes, this is pi n of x to the k, and this is the integral that we made. Okay, that's the algebraic parts now. And so let's check these. Let's check preliminaries. How many paths there are this is 1, 2, up to 2k, okay, on the integers. So at every step, okay, I want to make a path from here to here, that at every step it can go up by 1 or down by 1. Okay, how many there are? Okay, 2 to the 2k. It's just paths of length 2k. Okay, every time I can choose +1, -1. Clear? Yes. So, okay, there are 4 to the k paths of length 2k, each one +1 or -1. How many there are that finish exactly in 0? Okay, half of the time I have to choose +1, half of the time I can choose -1. So there are 2k, choose k. Yes? Is this clear? Yeah, okay. How many paths there are from 0 to 2k that maybe they come back to 0, but never become negative? So this is ck. 2k factorial, that's why I remembered. So why? Because how many there are? The easiest, you understand, yes? You can never go down, yes? The easiest way to compute it is that there are, how I compute it, it's 2k. So these are those that go from here to here, minus those that go from here to here, and at least once they are -1. Yes, those that never negative, that never touch the boundary below. Yes, it's all the paths between 0 and 2k minus those that touch at least in one point -1. Okay, so but let's count. It's very easy to count those that touch -1. So I drove me such a path, okay, that becomes negative. Okay, there will be a first time it is equal to -1, and then you see how many there are that are here are -1 exactly in the same point, and then finish in 0. Well, there are as many paths that go from -1 to 0 as there are that go from -1 to -2. Okay, so for each such path that finish in 0 and touches -1, I can draw one and only one path that starts in here and finishes in -2. Okay, there is a yeah, just by reflection. Yes, because if this one made +1, this one made -1, So in the how do I make a bijection between paths that start in 0 and finish in 0 but pass through -1, and paths that start in 0 and finish in -2? Okay, I wait until the first time. The bijection is as follows: I wait until the first time where the path is -1, any of the two. I mean, they will be the same for the two. And then this one went to 0, and every time this one made +1, the other one makes -1. And certainly this will finish at -2, and this will, because from -1 this increases 1, so this decreases 1. So of these, how many start in 0 and finish in -2? Okay, I have 2k positions, k plus 1, I need to put -1, k minus 1 times, I need to put +1. So it's 2k, choose k plus 1. And this, okay, this is 2k factorial over k factorial minus 2k factorial over k minus 1 factorial k plus 1 factorial. But if you write, you see, the 1 over k minus 1 over k plus 1 gives you k plus 1, and with the kind of, it's okay. This is a simple compute. Once you have this, it's clear that it's this. Okay. So ck, this Catalan number, is also the number of paths that start in 0, finish in 2k, and are always positive. Okay, how many paths start in 0, finish in 0, and never touch 0 in the middle? Like only do this, but in the middle never do this. Clear? Well, the first step, it will be up necessarily. The last step will be down necessarily. And then in the middle, you can do whatever, even touching like 1. So these are exactly ck minus 1. Yes, the first and the last are obliged. And in the middle, just I can never become, say, like -1. Yes, I just make a path, say, from the same level to the same level, never going down this level. It's exactly ck minus 1. Okay, okay. So this we will not use, but it's good for exercises. Maybe we can compute the generating function of Catalan numbers. So we can compute phi of z equal to the sum from 0 to infinity of ck z to the k. See, 0 is 1. Eh? So, okay, for k equals 0 is not the number of paths, is 1. It's unclear what it means, number of paths for k equals 0, so we take c0 equal 1. And, okay, the claim is that phi of z is, so it's 2z, 1 minus 4z. Why? So claim, okay? This is, we will not use it in this proof, but maybe it will become useful later. Proof. The proof is with all this, it's quite clear, because ck, I claim that ck is equal to the sum from 1 to k, yes, of c k minus j, c j minus 1. Why? Here there are too many pictures, but how can I count the positive paths from 0 to, okay, you can take this and do it by induction, but it's nicer to do as follow. How many paths there are from 0 to 2k that never become negative, okay? Okay. Let's, I say that
correct bracket sequences. We can count it like numbers of correct bracket sequences.
Bracket sequences?
Yeah, there's two brackets opening and closing, and we count on the correct and
yes, it is the same.
Yes.
But the problem is how to perform this bijection between the left and second bracket. You can think either on brackets or this path. This is the same.
Yes. Yeah, because okay, there are many characterizations, yes, of Catalan. We will see one more with trees in it. So I mean, if I have a path that goes from 0 to 0, there will be a first time, which could be 2k, yeah, but there will be a first time, which is certainly even, where it touches 0 again. So in this first chunk, it must be strictly positive. Okay? And then there is another path from 0 to 0. Yes, I just decompose the path with the first return to 0. Okay? So each path will have a first time it comes back to 0, and then another path from 0 to 0 where maybe it touches or doesn't touch again 0. So how many paths there are for each? So the sum, the ck is equal to the sum over j of the number of paths that touch again 0 for the first time into j. So ck must be equal to the sum over j of how many paths touch 0 for the first time into j, and that's cj minus 1, times how many paths go from 0 to 0, maybe or not touching again 0, from 2j to 2k, and that's ck minus j. Okay. So thanks to this, or you can prove it by induction from this explicit formula. So once we have this, this is easily established because well, first notice k. Let's take z less than 1/4, because of course the sum is not well defined. We check that ck is less than 4 to the k already. Because okay, if you want every time, there are 4 to the k paths in total, and certainly those that connect 0 to 2k as less than 4 to the k. So this is for z less than 1/4. This is an analytic function. Okay, it's an analytic function for z less than 1/4, and okay, and then so this is the proof. I'm continuing here. Okay, then we have that phi of z using this is the sum, okay, from 0 to infinity of z to the k, sum over j, 1 to k, ck minus j, cj minus 1. So let me put k equals 0 apart, so it's 1 plus. Then there is the sum from 1 to infinity. Okay, just copy the same thing. Sum from j from 1 to k, cj minus 1. I put 1z here, just, or maybe even here, 1z. Cj minus 1, ck minus j. And so this z to the k, I write it as z, k minus j. This z to the k, I write it as z. I wrote it a bit poorly. Z times z to the j minus 1 times z to the k minus j. Okay. Now, as you see, this is yeah. Okay, you have to rescale j plus 1 to j, but this is just the square. You see, is the number itself, z to that power, z to that power. This is just 1 plus z, phi of z square. This series is the square of this series. So, okay, so phi of z solves is a solution to that problem, so that we have that phi of z. We have that phi of z is equal to 1 plus z phi of z square. I'm a bit fast, you can trust me. If you do j equal to j minus 1, it works. So phi of z must be 1 plus or minus square root of 1 minus 4z over 2z. Z less than 1/4. But look, this function is analytical. So it's either plus or minus. Okay, it cannot be for some z1 and for some z another, because it's an analytic function. And certainly for z small enough is the minus, because this is this is less, for z say positive, this is less than 4 to the k is z to the k, which is 1 minus 4z. 1 divided by 1 minus 4z. So this function must be below. So if this z equal 1/4, something done like this. And if you check, if I take the minus, it's done like this and goes to 2 when z goes to 1/4. But if I take the plus, it's done like this. So for z small is certainly the minus, and since it's analytical, is the minus.
I guess for plus, it just goes to infinity. Because you have 1 plus.
In 0, you mean?
Yes.
In 0, yes, sorry. Yes, thanks. Sure, thank you. And it goes to infinity, and in any case, it's bigger. Yeah, so it's in particular, it's bigger than this. Yes, this is the sum of 4 to the k z to the k. Oh, this diverges, okay. But in any case, it's the one with the minus. Okay, so this is just generating function of Catalan numbers. Cool. This is I erase it, and we are back to prove the lemma. It's a nice combinatorial proof, but a bit long. So proof of lemma 1. Which is what is written, that the expected value of pi n of x to the k, the limit becomes the Catalan number, or 0 of k. So, okay, look, but what this thing? This thing is just the trace of the matrix to the k. Is this, yes, because the matrix to the k has eigenvalue lambda to the k, so it's just the trace of a to the k. So the expected value of pi n of x to the k, this is nothing but the expected value of the trace of the matrix x to the k. So this is 1 over n to 1 over n, because this would be just the sum of the eigenvalues, and there was 1 over n eigenvalues to the k. So it's 1 over n, the expected value. How do we write the power k of a matrix using the component? Is the sum over I1, I2, ik that go from 1 to n of x, I1, I2, x, I2, I3, blah, 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 x, ik, I1. Yes, for instance, if I take this and I make sum over I2, this is the component I1, I3 of x squared. So if I have to do, for instance, the trace of x squared, I have to do the sum of x, I1, I2, x, I2, I1, because for the trace I have to sum over the diagonal over I1 and I2. Yes? And then I have to take expected value. Okay? Huh?
Yes.
Yeah. Mm-hmm. So this is 1 over n, the sum over, let's denote this I, okay, of x. So these are like, okay, words. Each entry can be 1, 2 up to n, and they have length k. X, I1, I2, expected value of x, I1, I2, x, ik, I1. Good. Now, okay. You see here, there are a lot of zeros, yes? Every time this index, if here there is I1, I2, or I don't know, for instance, if there is something like expected, here there are all the possible, yes? xi1, xi2, xi2, xi3, for all the possible choices of I1, I2, I3 up to n, with the last one equal to the first. Okay, but if, so I don't know, for instance, there are terms like x1, x3, x3, x5, x, I don't know, x3, x1, x, x5, x7. Okay, I will have, I don't know, one of the term is like this for k equal to 4, provided n is at least 7. But you see, okay, this is 0 because it's true that this guy is equal to this guy, so it's x31 square. But the other ones are 0 because they are independent. So except these two that are equal, all the other are independent. So if a couple of index appears only one, this expected value is 0. Okay? Okay. This was just an exercise. Or maybe it can be useful for your exercises. And okay, then what I want to do is the following thing. I want first, so that's where we are. We want to estimate this sum and check. So this I are I1, I2, Ik, 1 to n, and we want to check that this thing will convert to the Catalan number, which is just where k is how many products I have here. Okay, so let's introduce on these indexes I1, I2, Ik, these couples I1, I2, Ik. Let's introduce this equivalence relation. Okay, I take that I is equivalent to I prime if like they are the same word of 1, 2 up to n up to changing the alphabet. So if so if there is a map phi from 1n to 1n such that I1 Ik is equal to phi of I1 prime, but if there is a bijection, phi of 1 prime k. So for instance, if I have 1, 2, 2, 3, 2, 4, okay, this is the same as, I don't know, 4, 5, 5, yet another 2, but again 5 and 1. Okay, because I just map 1, I call it 4, 2, I call it 5, 3, I call it 2. Okay, 2 was again 5, I already done, and 4 is 1. So these two are equivalent, but this is not equivalent to 1, 2, 3, 4, 5, and 6, because, okay, 1 I call it 1, 2 I call it 2, but then 2 I cannot call it 3, must be a bijection, okay? Okay, so let's call now, yes, so let's call.
So is it true that we have already proved that for odd k everything is 0 and that's all?
No, because xi, for instance, if here there is no, this only in the limit will be true, but otherwise no, because it could be that, for instance, there is some x to the cube. So if these random variables are symmetric, yes, because if it's odd, the one sum cannot be all even, the powers. But we only assume that the expected value is 0, but the distribution could be not symmetric. So the expected value of x to the cube could not be 0, for instance. So, okay. And okay, so let's just consider this equivalence relation. So this means that, like, what is a natural representative? If you give me one of these words, one that the first letter is called 1, then maybe there are a few ones. Then the first time appears a new letter, I call it 2. Then the first time appears, then maybe some 2 and 1s, but then the first time appears a third letter, I call it 3, and so on. This is a natural representative. Okay. Now I want to, so one of these sequences, I1 to Ik, up to this equivalence relation, I will call it a word. Okay. So the length of a word is just, so something like this will be just k, okay? Just how many entries there are. So if this word has k entries, I call it k, the length. And the size of the words is how many different letters. So if my word uses, for instance, this word uses, so for instance, length of this word is 6, and the size is 4, because I use 1, I use 2, I use 3, and I use 4. Okay. Of course, if these I are in relation, their length and their size must be the same. Okay. And I will call them WKS. Okay, this is space of words with length k plus 1, sorry for the plus 1, and here is k, and size s. Okay, so these are the words up to this equivalence. Okay, like you don't care, that have length and they are closed. Sorry, closed. So closed. Okay, so they have length k plus 1. Only s letters appears. And the closed means that the last letter is equal to the first one, like a bit we have in here, yes? Okay, I1. So you see, that's why I took the length k plus 1, because here I have I1, I2, k plus 1. Okay. Now, if I have such a word, I can associate to it a graph. We must remember, okay, this expression is easy to remember. So if I have a word, I can associate, if W is in WKS, I can associate with a graph which has S vertices, okay, that are the vertices of this graph are the letters that are in the word. Okay, so that with no loss of generality can be 1, 2, 3 up to S. Okay. Yes, and then there are edges between this. If 2 points are adjacent in the word, okay. So for instance, if I take as word 1, 2, 2, 3, 2, 1, 4, 4, okay. What are the edges? Not directed. They are not directed because we took this random variable symmetric, so it will not be important when we write if it's I1, I2, or I2, I1. So what is the edges in this graph? Okay, 1 from 1 to 2, then from 2 to 2, then again 2 to 2 is the same edge, 2 to 3, then 3 to 2 is already there, 2 to 1 is already here, 4 and 4, okay? This is this graph. This graph, so this is the graph connected to W. So this graph is connected because I have, I mean, this, sorry, the word must be closed. So 4 to 1. It's connected because my word span, there is this, I exactly draw the paths, the edges that span this word, and in this graph, there are only the letter used by W, no more, okay? And okay, and then we can call E W the edges of the graph. We can call EW C edges that are connecting. This just means that they have 2 different endpoints. And E loop W loop edges. These are just edges where the 2 endpoints are the same. Okay, so this is the union of this and this. Very well, and then okay, then if you remember, we just wrote it before that the expected value of pi n x to the k was 1 over n, the sum over all these I1, I2, Ik, so of this expected value of x, I1, I2, component I1, I2, x component Ik, I1. So this I can write as 1 over n. So I put these words, I1, or actually if you want this, I2, Ik, I1, I put them, I divide them by, so I have the space of all these guys, okay? Okay, where I think that they are I1, Ik, and again I1, to that equivalence relation, yes? I've divided all the i's in equivalence classes, okay? So instead of summing over all the I can sum over all the classes, and then for each class, the I in that class. Okay, because the equivalence relation is a partition of the space. Okay, so here I sum over all the possible size. A k is fixed, is this k here. The size cannot be more than the size, if you think for a moment, cannot be more than k, because if the size is because this word has length k plus 1, but the first and the last are the same, so more than k samples it cannot use. The sum over all the words in this equivalence class ks, and then I see all the I in the word w. Yes, like because w was a class of i's. So instead of summing over all the I, like I partition, and then all the I here plus all the I here, all the I here, and then I sum over all the elements of the partition, over all the words. Now the sum of the words I wrote as the sum over the possible size, the word with the fixed size. And then here there is, okay, the same, exactly the same thing. But then, maybe I should have introduced it before. For an edge in this word, so for this, let's call NEW number of times W passes, crosses, say E. So this means, for instance, in this case, you see, once the edge 1, 2, okay, I cross it 1 and I cross it twice. So here N1, 2 is 2. Then N1, 4 is also 2. And all the others are 1, yes? How many times when I follow the word, this word starts in 1, then goes to 2, then 3, then back to 2. Okay, so this is also 2, sorry. I pass it twice here, then to 1, and then to 4, then loops, and back to 1. Okay, so NEW is how many times? So this is 1 over n. So maybe we finish this computation. I hope to finish the limit today, but maybe we will not do it. Okay, so this sum over I, this is, so you see why this is useful, because I have here every time there is an edge in this word I, this word W actually. Here I will have x to the power of how many times that edge is crossed by the word W. Okay, so here I will have x, I don't know, edge x with the edge to the how many times it passes, and E. This clearly only depends, so since these are ID, only depends on the word, it doesn't depend on the order, because like the expected value of x35 square is equal to the expected value of x, I don't know, 1, 2 square, yes? It's indeed the expected value, okay? So, and then I have to take, however, the product, so in principle it's here, the product over all the edges. Okay, but now this, if you remember, now there are two. Okay, first they are independent. So if the edge is not the same, this expected value of the product is the product of the expected value. But also, if you remember, this was the distribution of this was 1 over square root of n, some y of diagonal, and 1 over square root of n, the distribution of some z on the diagonal. So the sum over all the I and W. And here, so by independence, I can take the product outside. So there is the product over the edges that are connecting of the expected value of, okay, x edge, but they all have the same. They have all the same distribution as y of the square root of n to the number of edges, the number of times I pass there. Sorry, n e w times the product on the edges that are loop of the expected value of z too small of the square root of n to the n e w. You want me to rewrite it? I just put like this product. The edges are the edges that are connecting and the edges that are loop. Why I split them? Because the law of x depends if xi is equal to xij is different if I is equal to j, or if I is equal or if I is different from j. So if I is different from j, it's like y over square root of n. Otherwise, okay, the square root of n, I can take it out. How many times is just how many of the x there were? So it's just k. So this is equal to 1 over, okay, one end was here. One end was here, and I have 1 plus k over 2. 1 plus k over 2 thanks to the square root of n. Then I have the sum over all the s, the sum over all the words in the equivalent class with length k and size s. Then this guy doesn't depend on I, only depends on the equivalent class. So it's this number times how many elements are in the equivalent class. How many elements are in the equivalent class? So words of length k when there are exactly s symbol. Well, like you remember that the equivalence class is just a relabeling of the alphabet. There will be, there are n, I have n possible symbols in total. I can use, but I can relabel like s must be relabeled and the others are free in some sense. So if you agree, I write it and you tell me if you agree. It's n factorial divided by n minus s factorial. The number of words where I can, because in this sum, each I went from 1 to n, okay? And I say that two words are equivalent if I can just relabel, so the length is k, but the length is not important. Here, I have n symbols, 1 to up to n. I can use s, what is, how many, if my words use s, it's simple, just I'm, like I don't know, I have word 1, 2, 3, 3, 3, 2, 1. Okay, length is not important. I use 3 symbols out of n possible. How many other words are equivalent to this? Okay, I can choose 1 in n different. I can call it in n different ways. 2, I can call in n times n minus 1, in n minus 1 different ways because 1 is already occupied. 3, I can recall it through an isomorphism phi in n minus 2 different ways. So it will be n times n minus 1 times n minus 2. So that's just n factorial divided by n minus s factorial. Okay, that's very standard combinatorial thing. So this is just the sum, and here is product over connecting edges of the expected value of y to the number of correcting edges, connecting the number I pass, sorry, on the number the word pass on the edge E, times product over loop edges of the word W of z to the power number of time my path pass on this. So it looks complicated, but okay, there are some numbers that depend on n. Then I have to sum over all the possible words done in this way. Okay, some factors that depends on the fact that you don't, it doesn't matter how you call each letter, 1, 2, 3, and so on, and to give you this factor. And here is just y was the random variable of diagonal. How many times there is the y in this product? This is the same of diagonal term in this product. Z to the power how many times there is the same diagonal term in this product. It's not rocket science. It's written in a bit complicated way, but it's done to compute. But that's it's not complicated. And now, if you see these guys, now it will become much nicer. these guys do not depend on n. This sum words nothing depends on n, but 1n to the 1 plus k over 2 n factorial over n minus s factorial. Okay, so let's rewrite this. And okay, we have 4 minutes. I'd like to make this number so that next time we can compute clearly without rewriting everything. So the expected value of pi n of x to the k is 1 to the n. So it's the sum s from 1 to k, 1 n to the 1 plus k over 2, n factorial, n minus s factorial. And then here I have expected value of y, no, sum over all the w of length k plus 1 closed and size s, of expected value of y to the number of times my word visit the edge E, product on the connecting edges, times product on the loop edges of the expected value of z to the power how many times my words crosses the edge E. Okay, this doesn't depend on n, but also up to here I didn't use that the expected value was 0 in reality. But now you see that if any of these edges is passed through only once, these expected values are 0. So here I can restrict to the words that cross each edge at least twice. This means that S, okay, if I didn't know anything on the expected value, that's it. But if a word has to cross each edge at least twice, and the total length of the pact is closed in this k plus 1, I cannot have more than 1 plus integral part of k over 2 different vertices, okay? Because otherwise with length k plus 1, I cannot make a closed loop that that pass twice on each edge, at least twice on each edge. Half, okay, you can transmit the plus 1 because it's where you start, but it's clear that half of the time you have to pass on the same edges, so you cannot make order k vertex, different symbols, okay? So, okay. But now this doesn't depend. Here you see, here we use that all this expected value, all the powers are bounded, yes, but are finite. But so in this is a number, it's some function of k and s. It doesn't depend on anything else, okay? And this is the only thing that depends on n, and this is a finite sum. K is fixed, okay? So. And factor, so this, I claim that this, the limit, when n goes to infinity, I claim that this limit will be 0 if k is odd. And otherwise is the same thing, but only in this, the whole sum only survives s equal to 1 plus k over 2 of the same thing. Because you see, okay, this doesn't depend on n, and what is the limit? When n goes to infinity of n factorial n minus s factorial n 1 plus k over 2. Okay, let's use Stirling. This is n to the n, e to the minus n, square root of 2 pi n times something that goes to 1.
I guess you can just cancel out most of the factorial, then you have a polynomial with s in the numerator.
Yes, this is e to the minus s exactly, plus s, but here it's okay, 2 pi n minus s, 1 plus O1. 1 plus O1 just means something that goes to 1. Now, so, and then there is n, to the 1 plus k over 2. So, yes, exactly, no, because, okay, let's make this minus s and to the s. You see that, okay, this goes to 1, the square roots, this goes to 1. E to the minus n goes away with minus n. Then there is e to the s, but here there is n minus s to the n minus s times n to the n minus s. And this goes to 1 over e to the minus s, yes, because this factor is 1 over 1 minus s over n to the n minus s. This by Euler, the minus s doesn't count. This goes to 1, but this is to the n. This goes to the e minus s. Cancel with e to the s. So it remains n to the s times n to the 1 plus k. So either s is 1 plus k, s is always no bigger than 1 plus k over 2. So if s, yeah, this was this very small. So there was n to the s that I removed from here, and there was n to the 1 plus k over 2 from here. So either s is exactly 1 plus k over 2, or it goes to 0. So all this term in this sum, this is a number, doesn't depend on n. All the term in this sum goes to 0, except when s is 1 plus k over 2. So if k is odd, it's never 1 plus k over 2. It's because if it's odd, the integral part is smaller. So only this term survives. Okay, so let's write this final formula, and next time, because it's very nice to see what words are in this w, k, k over. So we have that the limit, before the limit is not true, but the limit of the expected value of pi n x to the k is equal to the sum, only the term, the last term, of all the words in w, k, 1 plus k over 2. So okay, k is even, otherwise it's 0. And here I have the expected value of y and EW, expected value of z and EW. How many times? Products over the edges. Connecting, sorry, and products over connecting, and product over loop edges of the expected value of z to the n EW. So I leave you, if you want, one combinatorial exercise, which is the following. If you have a word which has length closed, okay, so it starts where it finishes. It has length k plus 1, so there are like k plus the last, which is the same as the first one, but it has exactly 1 plus k over 2 symbols, so k is even, okay, and there's exactly 1 plus k over 2 symbols, not less. Then the graph that you remember this graph, the vertexes are these n plus k 2 symbols, and there is an edge if the name of this vertex is adjacent in the word. Then this graph is a tree, doesn't have any loop. It cannot be done like this, for instance, or this. It can only be something like this. And the word, so must be like, I don't know, for example, 1, 2, 3, 4, and 5. Okay, it must be a tree. So the words can be something like 1, 2, 2, 3, 3, 2, 2, 4, 4, 2, 2, 5, 5, 1, or maybe longer, but still a tree. Okay? Can you do, so if you have a word closed with length k plus 1 and 1 plus k over 2 symbols, then the graph you built out of the word is a tree. A tree means it doesn't have any loop. Okay, okay, we check next time, but you can try to do this example. And then if there is no loop, certainly of diagonal doesn't count. This is empty, loop edge is empty, all the edges are connected, and we can also check that all these are 2. Like every edge, you pass through it exactly two times. If W is here, otherwise W wouldn't be here. And then okay, if W is here and this is non-zero, and then so you see that this is 1, and then because we assume that the variance was 1 of this random variable, so we just need to check that the size of these sets is the Catalan number. Okay, we will see next time, but just I wanted to tell you where is this circle coming from. Okay, so it's coming from these trees. Okay, sorry for being a bit late. We started a little bit late. Okay, thank you.